China's Semiconductor Revolution of 2025, the truth behind the tech breakthrough. A silent revolution is unfolding in semiconductor laboratories across China, one that defies conventional wisdom about technological innovation and global competition. While international attention remains focused on nanometer scaling races, Chinese engineers have been pursuing a different path altogether, achieving what industry analysts are calling the most significant architectural shift in computing since the microprocessor. This isn't about catching up, it's about leapfrogging entire generations of technology through fundamental physics breakthroughs and manufacturing innovations that challenge the very foundation of Western technological dominance. The implications extend far beyond national pride. They threaten to rewrite the global balance of technological power within our lifetime. Welcome everyone to Revo Now, where we decode tomorrow's hidden tech landscape, today. What we reveal in the next 9 minutes will fundamentally change how you understand technological innovation, global competition, and China's role in shaping our digital future. At Revo Now, we investigate beyond the headlines to bring you verified information about technological developments that truly matter. Our team analyzes patent filings, research papers, and manufacturing data to separate fact from speculation. Understanding this shift is crucial for anyone involved in technology, investing, or global business. The decisions made in boardrooms and government agencies today will determine market leadership for decades to come. This knowledge provides tangible advantages for career planning, investment strategies, and understanding the changing technological landscape. If you're committed to staying ahead of these developments, support our independent research. Press like, share this analysis with colleagues, and subscribe to Revo Now with notifications enabled. What we uncover next represents a fundamental shift in global technology competition. The established narrative surrounding semiconductor advancement focuses exclusively on transistor density, the relentless drive towards smaller nanometer processes. Industry leaders like TSMC, Samsung, and Intel have dominated this race, with their 3-nanometer and upcoming 2-nanometer technologies representing the cutting edge. This focus on scaling has created what many considered an insurmountable lead for Western-allied semiconductor manufacturers. Export controls and technology restrictions were designed to maintain this advantage by limiting access to extreme ultraviolet lithography, EUV systems, the multi-hundred-million-dollar machines required for advanced node manufacturing. The conventional wisdom suggested that without access to these tools, competitors would remain perpetually behind, unable to match the performance and efficiency of cutting-edge chips. This perspective dominated policy discussions and investment theses for years, creating a sense of technological inevitability. However, this narrow focus on a single metric of advancement created a critical blind spot in the global technology assessment. It failed to account for parallel innovation pathways that could achieve similar results through different means, a strategic oversight that is now becoming apparent. Behind the scenes, Chinese research institutions and semiconductor manufacturers have been pursuing a multi-faceted strategy that doesn't rely solely on traditional scaling. The most significant developments have emerged from research into advanced packaging, chiplet architectures, and materials science, areas where innovation can compensate for process node limitations. The Shanghai-based Institute of Microelectronics has published groundbreaking research on heterogeneous integration techniques that allow different chip components manufactured at various process nodes to perform as efficiently as single-die solutions at more advanced nodes. This approach, sometimes called more than more, represents a fundamental shift in design philosophy. Meanwhile, companies like Huawei's HiSilicon and SMIC have made substantial progress in specialized chip designs, optimized for specific workloads rather than general-purpose computing. By focusing on domain-specific architectures, they've achieved performance per watt metrics that compete with more advanced general-purpose processors for targeted applications like AI inference and 5G signal processing. These developments didn't emerge from isolation, but through coordinated efforts between academic institutions, state-supported research initiatives, and private sector implementation. The strategy has been to create an ecosystem of innovation that doesn't depend on any single technological breakthrough. The pace of advancement in these alternative approaches has accelerated dramatically due to several converging factors. First, the limitations of traditional scaling have become increasingly apparent, with diminishing returns from each new node transition. This has leveled the playing field somewhat, as all manufacturers face similar physics-based challenges. Second, artificial intelligence has revolutionized chip design itself. Chinese companies have deployed AI-powered design tools that can optimize architectures for specific purposes far more efficiently than human engineers. These systems can run millions of simulations to identify optimal configurations, compressing development cycles that previously took years into months. Third, the mature semiconductor ecosystem within China has reached a critical mass of expertise and manufacturing capability. While still behind in EUV-based manufacturing, Chinese foundries have achieved remarkable yields on older nodes and developed sophisticated packaging technologies that extract maximum performance from these processes. The combination of these factors has created a compounding effect where progress in one area accelerates advancement in others. This has enabled Chinese semiconductor efforts to advance at a pace that has surprised external observers who are focused exclusively on nanometer metrics. Evidence of this progress has been visible in recent product releases and technical publications for those who knew where to look. Huawei's recent smartphone processors, despite manufacturing constraints, have demonstrated performance characteristics that suggest sophisticated architectural innovations rather than mere process improvements. Academic papers from Chinese universities have detailed advances in areas like photonic computing interfaces, meme restore-based memory systems, and quantum-inspired algorithms that can run on conventional silicon. These aren't laboratory curiosities, but technologies that are being integrated into commercial products. The emerging pattern suggests a comprehensive strategy focused on system-level optimization rather than component-level superiority. By rethinking the entire computing stack from applications down to hardware, Chinese engineers have found opportunities for improvement that don't depend on winning the nanometer race. This approach has particular significance for artificial intelligence workloads, where specialized architectures can outperform general-purpose processors by orders of magnitude. As AI becomes increasingly central to computing, this architectural advantage may prove more valuable than raw process leadership. The culmination of these efforts is what industry analysts are calling the integrated silicon architecture approach. Rather than a single breakthrough, it represents a comprehensive methodology that combines several innovations into a cohesive system. The key elements include advanced packaging techniques that allow mixing and matching of different chiplet technologies, domain-specific processor designs optimized for particular workloads rather than general-purpose computing, AI-enhanced design tools that dramatically improve efficiency, and system-level optimization that considers the entire computing stack rather than individual components. Companies like Huawei and Phytium are implementing this approach in their latest processors. For specific applications, particularly artificial intelligence, telecommunications, and high-performance computing, these chips demonstrate competitive performance despite using manufacturing processes that are several generations behind industry leaders. The implications are profound. This approach could redefine how we measure technological advancement in semiconductors, shifting focus from transistor density to application-specific efficiency. It demonstrates that multiple paths to advancement exist and that leadership in one area doesn't guarantee overall superiority. For the global technology landscape, this means increased competition and diversification of technological approaches. It suggests a future where different regions might pursue different optimization strategies based on their particular needs, resources, and constraints. This development raises important questions about the future of technology development and global competition. Does this represent a viable alternative path to semiconductor advancement that could benefit other regions facing similar constraints? How will established industry leaders respond to this different approach to innovation? The emergence of multiple pathways to technological progress suggests a more diverse and competitive future for the semiconductor industry. This could lead to specialized processors optimized for particular applications rather than one-size-fits-all solutions, potentially driving innovation across multiple fronts. We want to hear your perspective on these developments. What do you believe are the most significant implications of this architectural approach to semiconductor advancement? Share your analysis in the comments below. This story isn't just about semiconductors. It's about the nature of innovation itself. It demonstrates that technological progress can follow multiple paths and that constraints can sometimes drive creativity rather than limit it. The future of computing may be more diverse and specialized than we previously imagined. The assumption that technological leadership must follow a single predetermined path has been successfully challenged. A new chapter in the history of computing is being written, and its ultimate shape remains to be determined. Thanks for watching. This is Revo Now, decoding tomorrow's hidden tech landscape today.